Right, so this seminar is about techniques of integration, and I was specifically asked to try and cover the crazier ones, but in order to do that I'm going to have to talk about all of them, so bear with me as I try and give you an overview of the whole topic of the techniques of integration. And this is my overview. I'll just do this. Okay, so you've learned 8 techniques of integration, but one of them doesn't really count as a technique, so it's called 0. So there's really only 7, and actually the 7th one doesn't really count either because you actually give up and do it numerically. And I haven't listed on there give up and ask Wolfram Alpha to do it because you can't do that in your exam. So these are the ones that you can do by hand. So I'm just going to talk through them first so that you can see how I've categorised them, because it's not exactly the same as what your lecturers do. And that's in general true when you're studying things for yourself or for the purposes of exams or other things. You often need to put it in a slightly different order than it was in the lectures. But this is the order I put it in. So the first technique 0 is just do it, when you can stare at it and go, oh, well, the answer is just a half of x squared. And there's a special technique in there that I will discuss shortly. The next one is to rewrite it, things like expanding brackets or using a trig identity, where you're not really doing anything to the integral per se, you're just rewriting it. For those, if there are more than 50 of you, but I have 50 copies of this on here, and it is also on the Maths Learning Centre's webpage too. So do be aware of that. So that's not really, you're not doing anything to the integral per se, you're just rewriting what's inside it so that you know how to integrate. The next technique is substitution, which is designed to be the reverse of the chain rule, but it's better than the reverse of the chain rule because it works even when what you've got isn't a direct consequence of the chain rule. So I'll talk through that. The next one is integration by parts, which is designed to be like the product rule for differentiation. So it's designed for things that are multiplied together. And there's several different tricks that you can do in by parts, and I've given them each a title, and we'll have a chat about them. And those are, just to go back to the whole thing, those are the basics of integration. So those techniques 0, 1, 2 and 3, they're the basics, and they're the ones you should always try first. In fact, you should try them in the order that I presented. So you don't necessarily have to actually physically write stuff down, but you should attempt, in your head at least, to see if you can just do it, and if that doesn't work, then see if rewriting it would help, and then if that doesn't work, then see if substitution would help, and if that doesn't work, then see if by parts helps. And in general, if you have to do both substitution and by parts, you should be doing the substitution first. So, because substitution's easier. So that's why it's in the order it is. And the other ones, going up on the other side, are in that order too because they're easier, but they're specifically designed for specific situations where it's really difficult to do integration. And the reason that I've gone up that way is because I want them to line up with the ones on the left. So reduction formula is a specific method for dealing with big powers, and it usually uses integration by parts in order to do it. So that's why I've lined it up here. Trig substitution is specifically designed for things with square roots in them. And it's a specific kind of substitution, so I put it next to substitution. And partial fractions is a way of dealing with polynomials over polynomials, but it's not really, you're not doing anything to the integral per se, you're just rewriting what's inside the integral. It's just a really fancy way of rewriting stuff, and so partial fractions is at that level, and then do it numerically is, well, you just give up. So that's in its own category, but it's the last one, so it has to go at the top. And also, there is a point at which if you know it's impossible, you can skip straight to do it numerically. Okay, so there's my list, and that's the order you should try things in. At least that's what I think, because I think it's the most useful thing to try. Because I believe that there's no point teaching people a whole lot of techniques unless you teach them how to choose which technique to do. And the maths exam writers are classic for just giving you a list of integrals and not telling you how to do them. Okay, so in your tutes you were told, do substitution and choose this substitution. They probably won't do that in the exam. So you need to be able to tell. Okay. Now, the bottom of this handout is my notes. Okay, so in the just do it category, there's things where you should just know the answer. And the first thing you should do is be able to know your derivatives as per this table, which I will just turn the focus on. This table is on the Maths Learning Centre webpage, and it's under derivatives, but it's also under integration, and it's also just under ordinary handouts, and there should be a copy of it in the Maths Learning Centre itself. And these are all the derivatives that you learn in Maths 1A. Okay, so it also has things from the fundamental theorem of calculus, but to focus on a couple, these things your lecturer expects you to be able to see and know the integrals straight away on this side here. So differentiation goes this way, integration goes this way. And your lecturer expects you to just know what the integral of these things are. Okay? They expect you to know that the integral of sec squared is tan. And they do expect you to know that the integral of sec x tan x is sec x, even though they haven't explicitly told you that anywhere, because it's in one of the tute questions. Okay? So it's really important to know that the derivative of sec x is sec x tan x, and that the integral of sec x tan x is sec x. They also expect you to be able to find the integral of a to the x. But there are other methods of doing that, so that's okay. And these ones in particular here are the ones that they really want you to be able to notice. The arc cos is less important, but definitely the arc sine, the arc tan. Your lecturers expect you, if you see 1 over x squared plus 1, for it to instantly flash in your mind, oh, arc tan. Okay? So get good at that, because it's really important. Okay? So anything that's got squares of variables and numbers added or subtracted, it should fire in your head that it's some sort of inverse trig thing, and that's what your lecturers expect. So I need to point that out now, because there's lots of people that I've talked to who see 1 over x squared plus 1 and don't have a clue what to do with it. Well, the integral of that is arc tan x. Okay, so that's the basics. If you see one of those, you just do it. Okay. The next one is that you're supposed to divide by the constant derivative. Now, technically, this comes under substitution, but your lecturer keeps doing it without telling you that it's substitution, and therefore you need to as well, because when they do the solutions for the exam, they won't take into account the whole process. They just want you to do it straight. So I'm actually going to write some examples to show you what I mean. So I call it divide by the constant derivative. I'm sure there is another word for it. And I know full well that in maths studies, this rule is taught explicitly in the Hazy and Hazy textbook. Okay? So you might not have noticed it at the time, but it's there. Okay? So I need to remind you. Okay, that's what I call it. I will put these notes on the website as well, so I'll scan them. So, just as an example, and this is the classic because you see it all the time, the integral of cos 2x dx. Okay, so the reasoning behind this is the same as the reasoning for the chain rule in differentiation. I go, well, if it was just an x, cover that up and pretend it's just an x, I would know what to do because the integral of cos is sine. Now let me just check that. The derivative of cos is minus sine. Okay, so it must be the plus. So the integral of cos is plus sine, and so I'm going to get sine plus c. But it's not an x, it's actually a 2x. And because the derivative of what is in that spot is a constant, I'm allowed to just divide by that constant as I go. If the derivative of what's in there is something other than a constant, so if it was an x squared inside there, I'd be stuffed. So you can't do this approach, you can't just divide by 2x. But if the derivative is a constant, then you can just divide by that constant. And that's all there is, and you do not have to show working, you just do it. e to the 3x plus 1, or maybe I'll whack a number in front of there. Well, the 5 will stay there because it's multiplied on. E to the x would integrate to give e to the x, because e doesn't, to the power of doesn't change. But it's not an x, it's a 3x plus 1, and the derivative of that is a constant, so I can just divide by the constant. And that is the answer. Right. What about this one? That one there. Same deal. If it was an x, it would be 1 over 1 plus x squared. So the integral would be arctan. But what's there is 3x, so I'll have to divide by the 3. And do be careful if what's there isn't a plain number. Something like that, that's an x on 2. If it was just an x, it would be 1 over 1 minus x squared under a root, and that means that would be arcsine. It's not an x, it's an x on 2, and the derivative of that is a half, so when I divide by the half, I'll get a 2. It's really good to just get good practice at noticing when that happens, especially for these ones which are new to you. Okay, so I just want to explicitly point that out because not everyone has that explicitly pointed out to them. So there it is. So that's the just do it category. Anything where you just know what to do, or if there's a constant next to it in a spot where you're not so sure, in a spot where if it was just an x it'd be okay, you can just divide by that constant. Alright, so the next strategy is to rewrite it. So you look at what's there in the integral, and perhaps if you expanded the brackets, or if you factorised it, it might be easier to do. Or it might involve trig, and you might use a trig identity. Now in your lecture notes, trig identity was in its own category in your lecture notes, but I sort of put it here because it's a fancy way of rewriting things. So, yeah, well. Something like that, the integral of x plus 1 squared dx. Well, it would just be simpler if I expanded it out, and then I would know what to do. So now that I've expanded it out, they're all just powers, so I can do each one separately. Power up by 1, divide by new power. Power up by 1, divide by new power. Power up by 1, divide by new power, plus c. Ta-da! Okay? So, I do want to point out, don't do substitution in that situation. It's not worth the effort. Just expand it out. Okay? Because you could try to do substitution. Now here's one that's less obvious. It's a trig identity. So I've got sine x squared. Okay, so the thing is that most things involving trig, a trig identity will get you somewhere where you need to be. You just need to think of the right one. And so you need to have in your head a list of trig identities that you think might be useful, and there will be on the Maths Learning Centre webpage with this a list of trig identities. It has totally more trig identities than you need, but the main ones you need are the sine squared plus cos squared is 1, and also the double angle formulas. So, Well, if I converted that to 1 minus sine squared, cos squared, I still wouldn't know what to do. So I probably have to use another trig identity, and the other one that's got sine squared in my head is this. And that's got the sine squared, which I've got here. So I should be able to rearrange it to get rid of the sine squared. But the cos x squared is 1 minus sine squared, so this would be this. So some people are able to remember this one directly. I can't. I always have to abstract it from the other rule. So that means that I should be able to rearrange that. If I put this over there and this over there and divide by 2, I should be able to get sine x squared is a half minus a half of cos 2x. So that means I can replace this with that. So the half is just a constant, so when you integrate a constant you attach an x to it. This half is multiplied on, so it'll still be there. The cos 2x, well, that'll go up to sine 2x, but I'll have to divide by the 2. And that's how you do it. I used a trig identity to convert it into something that I could do using my just do it list. Okay, there is one more. Well, there's several more. But there are plenty of examples of this on the Maths Learning Centre's YouTube channel. I'm only up to end of integration by substitution in my examples there. But there's quite a few on the rewrite it category. But I will do this one live because this is a crazier one. The integral of sine x cos 3x dx. Now it is actually possible to do this by parts, and you did it in one of your Maple TAs. But you can also do it by rewriting it because your lecturer assumes that you're familiar with various trig identities. And there is a trig identity that will arrange for sines and coses to be multiplied by each other, and it's the addition formula for sine. So sine of, I'm just going to write this soft because I'm going to rub it out. Sine of a plus b is sine a cos b plus cos a sine b. Okay, so sine puts the sines and coses together. If you do the cos formula, it will separate the sines and coses. It will put the sines with the sines and the coses with the coses. So that's how I remember it. I remember sine being sociable and cos being antisocial because cos doesn't like sine and it likes to separate the sines and the coses. That's my general approach to many things, like chemistry as well. Because you see all the elements on this side of the periodic table are generous and all the ones on that side are greedy. So anyway, I remember it in a personality approach, but other people have other methods of remembering it. And the other way of me checking it is if I put two A's in there instead of A and B, then it would come out to the double angle formula, and then I'd know I've got it right. So that would have a sine A cos B. So if my A was X and my B was 3X, then I'd get what I wanted. Okay, but that's the problem with it is I also have this cos x sine 3x, which doesn't match with that, but I can get rid of that by doing a different trig identity. Do the one with the subtraction. So it's exactly the same except it has a minus in the middle. And I can remember where the minus belongs because I know that if I put a negative into sine, it has to come out. So that sine of minus 3x came out to become a minus. So now if I add them together, I'll get sine of, now that's 4x, and sine of minus 2x. This plus this would give me 2 lots of sine x cos 3x. And this plus this would give me 0 because they cancel each other out. And so I'm nearly there. I can divide everything by 2. And actually, I know that I can bring minuses out as signs, so I reckon it might look a bit pretty if I did this. No, I'll just write it on its own line. Okay, cool. So that means when I do my integral, I can just do that, right? I know it seems like double handling to write it out again, and you could, if you wanted to, sub it direct into the integral earlier, but I'm the sort of person that if I do not write it out in full, I will get it wrong. So I just write it out in full. So with this one, the half will still be there because it's multiplied on. The sine will go up to minus cos, and the 4x I'll have to divide by the 4. The sine will go up to minus cos, and I'll have to divide by the 2. And so I get minus an 8 of cos 4x plus a quarter of cos 2x plus c. Okay, so that's the... I'll just give you a second to write that down. But in my list, you'll see in a minute, I've called it Make Your Own Trig Identity. Well, that's what I did. I used 2 other trig identities that I knew, and I put them together to make a new trig identity that matched exactly what I had. So I had to make my own trig identity to make that work. So all of those are under the rewrite it category. And there are even more. Just because it looks like a fraction doesn't mean that you can't rewrite it. There's a classic one more example of this. Like that. The integral of x plus 1 over x dx. Well, it looks hard at the moment, but if I just divided by x, which is what I've been told to do, x plus 1 all divided by x divided by x would be 1, 1 divided by x would be 1 over x. And now I can just integrate it. The integral of 1 is x, and the integral of 1 over x is ln x. So rewriting it can make something that looks difficult because it's a fraction into something easier. Okay, that's my rewrite it strategy. And as you can see, we've already been able to deal with quite a lot of integrals just by rewriting them. I'm going to cover this now, actually. So, being lecturer of the Maths Learning Centre, I do a lot of stuff on the fly every day, and so it happens when I give lectures. If I was actually lecturing Maths 1, I would probably be more organised. So I have 1 over x squared plus 10x plus 29 dx. And that looks really hard, but I do know that if I were, I do know one integral that has 1 over x squared plus something, and it's the one for arctan. 1 over 1 plus x squared, that would give me arctan. So there's at least one fraction that has a quadratic on the bottom that I do know how to deal with. And so it would seem reasonable to attempt to rewrite it to look like that. So what I'm going to do is I'm going to complete the square on the bottom. So I want to write it as x plus something squared plus something. So hopefully it's plus. And I just need to figure out what all the somethings are. I know that the thing that goes here has to be 10 divided by 2, because that's how it always works. Because if I expanded this out, I would get x squared plus 2 times whatever that was, times x, plus that squared. So this should be a 5. Because then if I expand it out, I'll get x squared plus 10x plus 25. You know, ignoring that top line. If I expanded this out, I get x squared plus 10x plus 25. But I haven't got a 25. I've got a 29. So there's 4 left over, and this 25 plus 4 comes from the 29. So now I've completed the square. Okay. Now that's still not going to look nice. If I replace the bottom with that, my arctan has 1 over something squared plus 1. So I should really just deal with this for a second and pull out the 4. That was a bad plan. I should have gone on to the next page. But that's okay. And I can bring that inside the square like that. So because it was a 4 outside, inside the square, you have to square root it as you come in. So now I've managed to write my original integral like this. So that quarter, that's really a quarter times something. And I know that if that was just an x, it would be 1 over x squared plus 1, which would be arctan. So it's going to be arctan x plus 5 on, oh sorry, that's a 2. It's going to be arctan x plus 5 on 2. And the derivative of that is a half, so I have to divide by the half, which means I have to times by 2. So I'm going to get a half Now, other people remember directly a formula for integrating 1 over that directly. I believe it's 1 over the root. If you have something like x squared plus a squared, I believe the integral is 1 over a arctan x on a, something like that. But I can never remember that, and I don't do this often enough, but I can complete the square. Okay, so that's just rewriting. You know, I haven't done a trig identity, really. I've just tried to make it look like something that I'm familiar with. All right. If they're really nice to you in the exam, they'll arrange for that final number over there to be a 1, so you don't have to deal with the pulling things out. Right. So as you can see, there's actually a lot of things under that category. And you don't have to necessarily remember them all at once. I mean, you do have to remember them all. But, sorry, people who are still writing. You don't have to remember them all at once. You just have to know that they belong under the rewrite it category. So, you know, they're the things to try first before you try anything fancy. Okay, right. So, next on the list is substitution. For when it might be easier if one thing was replaced by something else. So substitution is the chain rule for integration, and it's designed to replace the thing inside something else with just a u. Traditionally a u could be a theta or a t or whatever else you wanted it to be. But that's what it's for. And the hard bit is choosing what to choose to be u. And I have some advice for that. So you should find the most annoying bit. So if you were to do your integral, you look at it and said, gosh, if that bit inside the brackets was just u, gosh, this would be easier. That's the idea. That's really annoying, that bit. Oh no, there's something under the bottom of that fraction. If that was just x, or u in this case, it'd be so much easier. So find the bit that's the most annoying, that's inside something else, and call it u. And the other thing you should do is look for a derivative. So because it's to do with the chain rule, the way that it should work is that whatever you call u, the derivative of it ought to be in the integral already. If it's not, then you're probably just stuffed. But you should look to see if the derivative of what you make u is already there, because it should be already there. And then the other two bits of advice I'll have to get to in a minute. But you might need to rewrite it once you've chosen the substitution to make it possible. You might even have to do by parts later as well. And I've got this thing called work for substitution. Well, that means, well, I'll give you an example of that. So I should first tell you that there are many situations in which substitution could be used, but isn't necessary. So that's what this example is for. So that there, let's think about it. The most annoying bit is the fact that there's a 3x minus 1 on the bottom of that fraction. Because I would know what to do if it was just x. If that was just x, I would know what to do. It would be ln of, whatever's there. Okay, but the derivative of this thing is a constant, so I can just do it. I don't have to use substitution. I can go, well, if it was an x, it would be ln of whatever's there, and the thing that is there is 3x minus 1, and the derivative of that's a constant, so I can just divide by it. I don't have to do substitution. Unless I was explicitly told to, but your lecturers wouldn't do that. I just want to check something important. Oh, good, I am recording. Okay. It has happened to me before that I've gotten, an hour in and realised that I hadn't recorded the first hour. Okay, so you don't need substitution if the derivative of what you would make u is a constant. So this example is going to deliberately be a little more... let me think about this. Yeah. This is a classic example. So I've got x, and then in brackets 2x plus 1 to the power of 15. This is a classic substitution example. Okay, so presumably you could, if you really wanted to, expand it out. All right, and just do each power separately. It's perfectly possible, but 15 is a bit extreme, so we won't do that. But if it was just 2x plus 1 squared, I'd probably expand it out. Okay, but since it's not, and that's going to be harder, I will use substitution. So the most annoying bit is the fact that this is inside this power, and so I'm going to call that u. So the stages in a substitution are that first you should choose what u is and write down a statement that says let u be equal to whatever, and then you should deal with the dx. So everything that's here has to be replaced with something involving u. So you're really used to probably seeing this symbol and this symbol together as like brackets that tell you what to do to what's inside. So you don't normally see the dx as an object in its own right, it's just the completing bracket for your integration. Well, what we're going to do in substitution is going to divorce the dx from the integral sign and just look at what's there. Okay? So this and this dx is going to be considered as an object in its own right that I can multiply by that other stuff. So it's actually x times 2x plus 1 to the 15 times dx. That's why it's so important, and that's why school teachers and lecturers and pretty much everyone else who tries to teach you integration are so focused on making sure you write the dx. Because it's an actual object that really is there, it's not just a bracket. And without it, I can do my substitution wrong. So I'm going to try and figure out what dx is in terms of du so that I can sub it in. So to do that, I'm going to have to differentiate. So I'll just look at this and I'll differentiate it in the ordinary way. U is my function, the derivative of 2x plus 1 is 2. And then here's the fancy bit. one way of imagining a derivative is imagining it as saying, well, a very tiny change in u is related to a very tiny change in x in this way. So a tiny change in u would correspond to twice a matching tiny change in x. That's what this says. And so I'm allowed to do this because it's okay in substitution. What I'm literally doing here is remarking my x-axis in terms of u. Okay, so I used to have, when x was 0, u comes out to 1, so I have a new marking. It's like having a ruler that's got centimetres on one side and inches on the other. Well, I've got a ruler that's got x's on one side and u's on the other. And I know that if I change x by a little bit, it's actually going to cause u to change by quite a lot because u is bigger than x. It's 2 times x. So the markings for u are twice as far apart. So I'm going to, actually they're half the distance apart. Anyway, it's hard to tell without drawing the picture. So that's what's going on, and then I look to see if I can find this in my integral, and I can't. The 2's missing, but I can always fix that by doing this. Now I know that a lot of you, when you do substitution, have a different way of approaching it to what I'm doing here. A lot of people will write it as a dx equals, and some people will do a du on dx and like cancel stuff out. I do it this way because this is how I was taught. And it makes sense to me. Okay, so let's just go back to our original integral and have a look at where we've been. We know what to do with the dx, okay? It's a half of du. And we know what to do with this. That's u. But we've got this bit left over. And that's what I mean by work the substitution. I have a little bit more work to do, beginning with my original substitution of u equals 2x plus 1 in order to deal with that x. So I'm going to go back to my original substitution and figure out what x is in terms of u so that I can sub in u's there. So okay, so now I can deal with the x because it's half of u minus 1. Now I should tell you, to be grammatically correct, you need to actually start with your original integral again on your next line. You can skip it and no one will mind that much, but in terms of grammar, it works better. Because if you just start with an equals, there's nothing for it to be equal to. So grammatically, you should start with this. And the other reason is, it helps me to remember what I'm doing. Because I can go to each piece of this and replace it. The x is replaced with half of u minus 1. The 2x plus 1 is replaced with u. The dx is replaced with a half of du. And then I expand it all out. So now I've turned it into something, it's a brand new integral. I can ignore where it came from. That's a times, not a plus, by the way. I can ignore where it came from and go back to my original strategies of rewriting it and just doing it, and I still can't just do it, so I'm going to have to rewrite it. I've got a quarter, and I can bring the u to the 15 in, right? So I'm going to have a quarter of u to the 16 minus a quarter of u to the 15 if I expand that out. And that I can do. The quarter will still be there. The 16 will go up to 17 and I'll divide by the new power. The quarter will still be there. The 15 will go up to 16 and I'll divide by the new power. 34, 68. Okay, so that's the second stage. Okay, the second stage, well, the third stage, there's lots of stages. At some later stage than the first stage, this is where we've managed to get it, we've managed to actually do our integral, but it's still in terms of u, and we should go back to put it in terms of the original function again. that's what u really is. This is a classic substitution problem that forces you to work that substitution, to do a little bit of extra work to get rid of those leftover x's. Okay. Before I move on, because this is fine, does anyone have any specific worries about substitution that they wanted to bring up bravely now in front of these people here that you would like me to cover at this moment before I move on from substitution? Yeah?
Oh, no, actually, I think that's related to trig substitution.
Okay, so I will do trig substitution, I really will. I might do it now, actually, and do this out of order so that you can see how it's done. And that's a good point, because I did promise I would do it, and we're already almost an hour in. So
should I ask that question in trig substitution?
Ask it now.
Oh, okay. When you do trig substitution and say you get your answer in terms of a sine or a cos, how do you know when you have to then put it back into terms of x from the sine, like do the triangle?
Yeah. So for those listening on the video and everyone else who might not have heard in the room, when you're doing trig substitution and you get to the end and you've got everything in terms of theta or u or something, how do you put the x's back and how do you tell if you're supposed to?
Yep.
Okay, cool. I will do that. Before I do, how do people feel about doing substitution on a definite integral? Can you follow through that working and get it right? Okay, cool. Because there are at least three approaches. Yep.
So if you're doing like a definite integral and you're doing like substitution with trig, let's say, can you work out in terms of u and then substitute your, say, angles back in after in terms of x?
Yes. So I've just had a question of, can you figure things out in terms of u and then substitute things, the x's in at the end? Yes, you can. But you just have to be careful with your notation. So I'll just do one here, a short one of ordinary substitution. Give me a second. This will not probably turn out well, but we'll run with it. Okay. This is a classic substitution problem because it looks sort of arctan-ish at the moment because of the x squared plus 1 on the bottom, but arctan has a 1 on the top. So being able to distinguish when you should be rewriting it in terms of arctan and when you should be doing substitution is important. I would see if I can just do it, and it would have to be a 1 there, and it's not. So I'm going to have to move to a later step. I can't rewrite it. Completing the square on the bottom is just not going to do anything. It's already complete. So I'm going to have to do substitution. And that should work because the derivative of the bottom is almost the top. Okay, so that's what I mean when I say look for a derivative. Okay, there are at least 3 approaches to this. I will attempt to do all 3 so that you can see them. There are at least 3 approaches to this, but they all start in the same place. Let u be x squared plus 1, and the first thing I should do before I do anything else is figure out what du on dx is, and then I need to rearrange this in some way to try and deal with the dx. Okay, so I go back to my original integral, and I look for 2x dx. Now, this dx is really a dx over 1 as a fraction, so the x dx is on the top there. So I do have an x dx, but not a 2x dx, but that's okay, I can always deal with the number. Okay, so that means that this bit here, I've dealt with that. The x dx is equal to a half of du. So I'm always looking to try and combine as much stuff with the dx as I can so that it just disappears when I replace it with the du. I've dealt with this, that's u. So the only thing left is to deal with the 0 and the 1. Because that 0 and the 1 are referring to x, they're not referring to u. So I just need to figure out what to do with them. And there are 3 approaches to dealing with that. So the first approach is to do it as an indefinite integral. So the x dx was a half of du, and the x squared plus 1 was u, which is ln half of ln u plus c. ln 0 doesn't exist, but that's okay because u isn't 0, x is 0. Okay, like that, and then actually sub the x's back in, ln of x squared plus 1. And then you can go, well, therefore the integral from 0 to 1 of x over x squared plus 1 must be half of ln x squared plus 1, 0 to 1. Okay, so just figure out the indefinite integral and then do the definite integral. So that's one method. So half of 1 squared plus 1 minus a half of ln 0 squared plus 1. Do remember, it's really important to sub in the 0 properly, because a lot of people at this stage would actually go stuff minus 0 and they would have gotten it wrong. Okay, because it's not 0, it's ln of 1, which actually happens to be 0 in this case, but sometimes it's not. So this is a half of ln 2 minus a half of 0, so it's a half of ln 2. Okay, so that's an answer, that's one approach. Approach 2 is to not change the x, the 0 and the 1, but just keep them in the integral as you go. So I can, if I want to, change this. So the x dx was a half of du, and the x squared plus 1 is u, and not change those numbers, but I need to remind the reader that those numbers still refer to x and they don't refer to u, so I've got that x is 0 and x is 1. And as long as I actually tell the reader that those are x's and not u's, it's okay to just run this way. So now those x's are really x's because I put the x's back in. So until you put the x's back, you have to remind the reader that those numbers refer to x. Okay, so that's a second approach, which has slightly less working overall. And the third approach is the one preferred by most maths lecturers, but they will accept any of these, just to point out, so you pick one that works for you. The third approach is to, before you do the integral, figure out what those x's refer to. So if x equals 0, I know that u is 2x plus 1, and so if I sub in 0, I get 1. And if x equals 1, I know that u is 2x plus 1, so I would sub in sorry, it's not 2x plus 1, it's x squared plus 1. That 2x plus 1 was from the other example. Yay! Sorry about that. 1 squared plus 1, which is 2. And then my integral can be changed all in one go. So every piece can be done. 0, 1, x, getting ahead of myself, x squared plus 1 dx. So the x equals 0 becomes a u equals 1, according to this. The x equals 1 becomes a u equals 2. The x dx becomes a half of du. The x squared plus 1 becomes a u. And so I'll get the integral of a half of ln u from 1 to 2, and then I'll just sub them in. my absolute value sign disappeared because that 2 is positive. That's the preferred method of a maths lecturer. Okay? But you pick what you want. And you can switch and change. You don't always have to use the same method. Use whatever works for you today. I wonder if that will work. Okay. I don't know if you feel hot. I do, but I've been talking straight for an hour, so suck it up. Okay. Gosh, I sound really callous then. Right. That's substitution, and it's good to know in any situation what you would do if it was a definite integral and what we would do if it was an indefinite integral, and that's what you do if it's definite. And you can use any of those approaches in trig substitution, which I will do now out of order because we're on it at the moment. Okay, so trig substitution is designed for powers and roots of what I call Pythagoras-ish expressions. So something squared plus or minus something squared, where one of the somethings is a variable and the other one's a number. Okay, so that's what we're looking for. So things like 1 minus x squared or x squared plus 1, those sorts of things. Or x squared minus 1, that's what trig substitution is for. Specifically when you have powers like cubed and roots, especially the roots, and when you've already checked to see if ordinary substitution isn't going to work. Okay, so you do need to first check if ordinary substitution is going to work. So just as that example I did just then, it does have a Pythagoras-ish sort of thing in it, an x squared plus 1. But I don't need to do trig substitution because ordinary substitution will do the trick perfectly well because the top is the derivative of the bottom. Okay, so you need to check that first or you've wasted all that time because trig substitution takes ages. Okay.
Will trig substitution be worth one exam? Is that a way to tell?
Trig substitutions will normally be worth more, yes. So the question was, can you tell it's trig substitution by the number of marks awarded to it? Probably. Trig substitution requires you to know how to do rewrite it by trig identity, usually, and various other manipulations, and so it does test multiple things at once, and so it will be worth more marks if it's a trig substitution. Okay, so I've got some advice. I use a trig identity to decide which trig substitution to do. Okay, so I simultaneously start working on the substitution and figure out which substitution to do at the same time, rather than having a list in my head. A lot of people have, well, if I see an a squared minus x squared, I'll do this substitution. I just don't think that way, because that's too hard. There are too many things in my head all at once. So I use trig identities to help me decide which one. You're going to have to work the substitution in order to put the substitution in. After you've done the dx on d whatever, you're going to need to do some work to deal with all the other leftover bits. And you're going to have to work the substitution to get x back at the end as well. Okay, so you need to leave quite a lot of space between your original integral and when you actually start putting the substitution in, so that there's plenty of room to do everything you need. Now I'm going to refer to my handy dandy book of integration examples. Yep, let's do this one. The integral of 5x squared over root 9 minus x squared dx. Okay, so I should just run through my list. Can I just do it? No. Would rewriting it help? Yeah, that root is not going to expand out over those things, so that's just not going to work. Ordinary substitution, well, ordinary substitution, I would make that the u, because that's the most annoying bit. And then the derivative of that should be there somewhere, so I would get like a 5, the 5x would work, but there'd still be an x left over. and that x would be like root something. No, I'm just going to get more roots if I do that. So no, ordinary substitution isn't going to help. I'll just get even more roots elsewhere, so that's not going to help. And by parts might possibly work, actually, but I know also there's a list in my head of special cases, and if I see something that's got a root in it like that, I'm fairly sure it's going to be trig substitution. So this root, the whole point of trig substitution is to make that square root go away. That's what it's for. So we're going to have to use a trig identity to turn whatever's under that square root into a single thing squared. Okay? So this is the philosophy behind it. So I'm going to leave a lot of space here to do the work of the substitution itself. So I'm going to leave a space here to do my du on dx. Okay? And I'm going to start looking at this. I want that to match with a trig identity. And my trig identities tend to have variables in them, like sin x squared plus cos x squared equals 1. But if I rearrange that, I can arrange it to have a number and a variable. Okay? And that's what I'm thinking about. So ignoring the 9 and just treating it as a number and thinking maybe a 1, 1 minus something squared, cool, 1 minus sine squared would be cos squared. That's the trig identity that's going to be helpful to me. Okay? So I really would like that x to be like a sine squared, only ordinary sine squared is not going to cut it. Let's just think this through. Okay, there's no trig identity for 9 minus sine squared, but there is one for 1 minus sine squared, so if they both had a 9, that would be awesome, because I could bring the 9 out. Sorry?
That's not u.
Yes.
Okay.
I use u, because I use u's for all substitutions. And my thetas look stupid, so, because I write my o's backwards, so my thetas look really stupid, so I am, yeah. Okay, so 9 minus 9u squared. What that means is I would be able to bring out my 9, and that would become a 9 cos u squared. And that would be really great, because then if I square rooted that, the 9 would become a 3, and the cos u would become, a cos u squared would become a cos u, and I'd make magically make my square root go away. So in order for this to be 9 sine u, I'm going to have to be like 3 sine u for my x. That's how I decide. And I know that sounds like it's a bit of jiggery-pokery, but you know, I had to do something that I could do in my first year exam. And so that's how I think about it. Actually, you'll notice that often what I'll do is I will start here and work backwards in both directions. And I'll often actually start with sine squared plus cos squared equals 1 and rearrange that. So, yes. Okay, so there we are. So my x has to be 3 sine u. There's a technical point here. I have to technically make u be between minus pi on 2 and plus pi on 2. Because arc sine is only defined there. So, but it's okay to skip that because no one will care. I know that sounds really dodgy, doesn't it? It's like if no one sees me do it, I didn't really do it wrong. So it's okay to skip that because it will work anyway. Okay, let x be 3 sine u. And now I'm going to deal with my dx. So normally what I do is I do du on dx, but I can get a dx by doing dx on du, and that's going to be heaps easier. So dx on du is 3 cos u. And that's why I chose sine instead of cos, because if I'd chosen x equals 3 cos u, the trig identity would still have worked, but when I differentiated, I would have got a minus, and it's never a good plan to introduce more minuses because you'll just lose them somewhere else. So everyone knows that the more minuses, the more chance there is of an error. So we're going to do it with a sign. Okay, and so that's telling me that my dx is 3 cos u du. Okay, so I can literally just look at my dx and go, yep, replace that whole thing with 3 cos u du. Now my root 9 minus x squared, just starting over here, is root 9 cos u squared, which is 3 cos u. Okay, cool. You'll note something that I've done here. I have deliberately not done my working inside my integral. Some people would have subbed this in under the root sign. I figure out what the root is before I put it in. Because then I can replace this entire thing in one go without having to keep writing integral signs over and over. Okay, so that leaves me with the 5x squared that needs to be dealt with. Okay, so let's just think this through. I will just start again. Now, we've got that x was 3 sine u, and I need to figure out what 5x squared is. So x squared would be 9 sine u squared, and so therefore 5x squared would be 45 sine u squared. So now I can replace the 5x squared as well. Okay, all right, I think I might be able to put it all in now because I've now dealt with the 5x squared. Okay, all the bits are done. Excellent. However, I will just leave some more space here just in case I need to do some more working later. So the 5x squared is 45 sine u squared. All of that root there was 3 cos u. And the dx was 3 cos u du. Which conveniently cancels with the bottom. Magic! You'd think that I designed it that way. So, now I need to integrate 45 sine u squared. Damn. I have to use a trig identity to do that. I did a sine squared before in my earlier example, didn't I? Just a second. Yeah, I did. Look, there it is. Sine squared. So I could just use my answer, but it's more illustrative to not. So point being, you need to ignore the fact that this came from x's and just look at the integral you've got and see how you could do that. And the first thing to check is to see if I can rewrite it in a certain way. And I know I can write a sine squared in terms of cos 2. So I'm going to go back to my working back here and put it in beforehand. The reason I'm going to do that is because it's going to make my life easier later. So my sine u comes from a cos 2u, doesn't it? Okay, so cos 2u would be cos u squared minus sine u, right, which is 1 minus 2 sine u squared. And so I'll get that sine u squared would be a half minus a half of cos 2u. And so 45 sine u squared would be 45 on 2 minus 45 on 2 cos 2u. Okay. So let's see. My 45 sine u squared is 45 on 2 minus 45 on 2 cos 2u du, which is 40, the integral sign's gone, which is 45 on 2u minus 45 on 2, the cos would go up to sine, and the 2u I'd have to divide by the 2, so that'd be a 4 there. And here we are. We have now integrated it. The integral sign's gone. Now we just need to deal with the sine 2u. Okay. Well, let's just check. Maybe I've written down what sine 2u is already. No. Okay. Well, I'll go back to the space that I left in my working. Sine 2u is 2 sine u cos u. Now let's see. Oh look, x is 3 sine u. That means that sine u is x on 3. And I can sub that in here. And cos u, just a second, didn't we just say earlier that root 9 minus x squared was 3 cos u? So that means that a third of root 9 minus x squared is cos u. And so I've got 2/9 of x root 9 minus x squared. And so therefore now, let's put the 45 on 4 in now too. 45 divided by 9 would be 5. 5 on 2x root 9 minus x squared. Okay, so I've got 45 on 2. I'll just deal with that in a second too. Nope. It was 5 on 2x root 9 minus x squared plus c. Now u, from here, u would be arcsine x on 3. Cool. Arcsine x on 3. Ta-da! Okay. Trig substitution's really hard. Yep.
And how do you know that you can leave it as arcsine x on 3 and you don't have to put it into x on something square root?
Because it doesn't involve a sine already. So, because this is a plain u all on its own, and it's not trapped inside a sine or a cos, I have to leave it as arcsine. That's the rule.
Oh, okay.
Yeah. So, if it's a plain u that's not inside a sine or a cos, it has to be the arc something, or a tan. If it's sine or cos of u already, you have to find out what that is earlier in your working. Now you'll notice I didn't use any triangles to do this. I'm sorry if that's your preferred approach, but the triangles, they're lovely, but I just get confused. So, especially when I get a sine 2u. And I don't know, I can't get that from a triangle, so I have to get it from a trig identity. I will illustrate something though. What a lot of people do is they think through it in terms, I can do it, alternatively. You could go, that root 9 minus x squared looks like a Pythagoras thing. And if I was doing a Pythagoras' theorem sort of stuff, I would have a minus on the short side of the triangle. So I need to have root 9 minus x squared on the short side because it's got a minus. If it had a plus, I'd put it on the long side. And that means that must be 3 squared, and this must be x squared. So you do that. And so you can make a triangle like that. That's the other way I have of doing it. I look at my 9 minus x squared and I think, well, that would be from doing the short side of a Pythagoras' theorem. And then I arrange my angle u to be in a place so that I get something nice. And so I want x to be, well, I'm not sure yet, but I will put it here just because that seems nice. If I put my u there, then I get that sine u is x on 3, cos u is root 9 minus x squared on 3, and I could even figure out tan u if I wanted, which would be x on 9 minus x squared, root 9 minus x squared. Okay, so lots of people do it that way, and that automatically produces your sine and your cos, and you also You don't have to do your trig identities to make it work. But interestingly, even though I normally think in pictures, for this I don't, and that's just the way it is. So you could have done it that way, and then from here figured out your, from there gotten your x equals 3 sine u, and from there your dx is 3 cos u du. And I would still need to figure out my 5x squared. So I will make that prettier. So I could have done, you know, sine u is x on 3. And also I could have gotten from there that u is arc sine x on 3, and subbed everything in, and I would still need to go, well, x is 3 sine u, so x squared is 9 sine u squared, and so 5x squared is 45 sine u squared. And now I've got all the pieces I need to sub it in. I've got this bit, and this bit, and this bit, and I can sub everything in. So that's an alternative approach if you like the triangle thing. So if you do want to talk about that more, that's why we have a Maths Learning Centre. You could ask the tutors, look, I've seen Trig Identity, I've seen Trig Substitution using only Trig Identities, and I've seen it using triangles. Can you explain, and pick one that you like and ask the tutor to explain one of them to you. They might not know both, but if I'm there, you can always they'll refer to me. So, yeah. Okay. One thing with a long and complex process is to mark out the pieces so that you can know when you're halfway. So with the trig substitution, there was the bit where I figured out what the substitution was, and there was the bit where I did all this working to help me with my substitution, and then there was the bit where I had to do the trig identity, and then there was the bit where I put it back. If you can keep yourself in that list and say, these are the parts that I had to do, then at least you can keep track so that you don't lose your way halfway. But one of the advantages of an exam is that you will get marks for only going halfway. So that's a good thing. Now, where was I up to? All right. Integration by parts. When I learned trig substitution first at school, we did it when we did ordinary substitution. We didn't leave it till later. Don't know if that's a good idea or not, but it connects nicely. And that's why I always use u, because I always use u for all substitutions unless it's already u. Okay, so integration by parts is designed for products of functions. It's the product rule for integration. And it's the third one on the list. So after trying to just do it, and after rewriting it, and after trying substitution, then by parts is your next option. Yes?
Do we have to know how to do hyperbolic substitution?
Don't think in the exam usually. There has not been a hyperbolic trig substitution in the exam for 15 years, so I'm fairly sure. No time like the present! So no, I don't think you have to do a hyperbolic trig substitution in the exam. I can't guarantee that, but Nick Bookdale was your lecturer for calculus, wasn't he?
Yes.
All right, he'll be in the Maths Learning Centre tomorrow. You can ask him. Or you could email him and say, will there be? And he'll probably say no. But I just, no, yeah. Since it's usually only in a tute, right? Yeah. So they can assess stuff in tutes, but they often don't. So, yeah. Hyperbolic trig substitutions are fun, but you have to know your hyperbolic trig identities. And you don't, yeah. So we'll just say no, right? Okay. By parts is the product rule for integration. And just like with substitution, you have to pick which bit is which, okay? So in substitution you have to go, which bit is u? And you need strategies for choosing the right u. And by parts is another one of those. You have to choose which bit is which. So there's going to be two pieces in the by parts. One part is going to get integrated and the other part is going to get differentiated. And so you need to choose which bit to integrate and which bit to differentiate. And my rules are, you should only integrate things you can integrate. It's a nice plan, okay? So if you do not already know off the top of your head the integral of something, do not choose it to be the thing that you integrate. That's a waste of time, okay? So x ln x, for example, I've seen people integrate the ln x. It's like, really? It works actually. No, it doesn't, just gets awful quick. And the second step is to aim to make it simpler. So the thing that you differentiate should eventually disappear. That's your hope. If, however, neither of those apply, just pick whichever ones you want, and you might need to do it more than once. And there are two fancy strategies. Try doing 1 times or going around in circles. So, can I just check something? Your lecturer, did they write it like this? No? Good. That's crap. Sometimes they do, so I just wanted to check. Okay. So it's designed for things that are products. I will call them F and G. You can call them U and V or whatever you want. Now there's supposed to be a dash, but I'm holding that in reserve for a minute because I want to show you how I remember this formula. It's got an FG here, and it's got an FG here, and it's got an FG here, and that's a minus. And one of these F's and G's, one of them has a prime, an apostrophe, and the other one has a prime over here, has a dash over here. It doesn't matter which one you pick as long as the other one has the dash on the other side. It took me years to come up with months. I think I figured it out in first year, but it took me a long time to come up with a method that I could remember it. So when I write this, I usually write the FG, the FG, the FG, fill in the integral signs and the minus, and then put the dashes in. Okay, so it could be this, or it's just as easily be this. Doesn't matter. As long as one has a dash on one side and the other one has a dash on the other. Now that may muck up some of your processes for doing it, because people in the Maths Learning Centre are saying, which one's G? And I go, I don't know. The second one's always G. It's just which one has a dash is the real question, because that's how I think about it. So if you always put G as the one with the dash, you're going to have to reorder the things that are there in your integral. Okay, now I should point out as well that by parts has a definite integral version. So if you're doing definite integrals, then this FG is the result of doing an integral, so it has to have your square bracket thing in it. So don't forget to do that, because people do. Okay. This is a classic example, the integral of x cos x dx. Alright, so I know that this is going to be f and g for some f and g. And I know that when I integrate it, it's going to give me this. My question is, where am I going to put my dashes? So I think about it. I need to integrate what I can. I do not know how to, well, I know how to integrate cos. It's fairly simple. I know how to integrate x. Okay, so that's not going to help. So the next stage is to aim to make it simpler. If I integrate the x, it'll go up to an x squared, and my cos will remain trig-ish, and so that's just going to be worse. But if I differentiate the x, it'll become a constant, and I'll be able to deal with that. So I should choose this to be the one that gets differentiated, and therefore the other one gets integrated. If you're the sort of person who always does the g as the one to be integrated, if you had them the other way around, you may have had to switch the order to make it work for you. So what I have here is that f is x and g dashed is cos x. And so f dashed is 1, and the integral of g dashed is g, which is sine x. The reason I write it this way is that in my head integration is up and differentiation is down. So that's why I write it this way, so that my dashes are both at the bottom. Some people write it the other way, but that's just that whatever your personal preference is. So now I just sub all these in. Right, so the f is x, and the g is sine x, and the f dash is 1, and the g is still sine x. And the integral of 1 sine x is minus cos x. Oh, no dx, sorry, plus c. Ta-da! That's integration by parts at the most basic level. So I told you that there's a couple of fancy strategies. So there's the fancy strategy of try 1 times. The integral of arctan x. Now if I had seen an x arctan x, I would automatically know that I couldn't integrate the arctan, so it would not be the one that gets integrated. Same deal though, I don't know how to integrate arctan. I do, however, know that, and substitution is not going to help, so I do, however, know that I could put a 1 times here, and now it's f times g. Now I can't integrate the arctan because I don't know how. So it's going to have to be this one with the dash. See how it matches with my way of thinking? I just write the f and g down and they are whatever they're underneath. So my f dash is 1 and my g is arctan. So my f integrated would be x, and my derivative of arctan is 1 over 1 plus x squared. So f is x, g is arctan, f is x, g dashed is 1 over 1 plus x squared. And now I have a brand new integral to do. So I treat it like a brand new integral, and I go back to trying my other methods. So first I look to see if I can just do it. Nah. Then I look to see if I can rewrite it in some way. No, that's probably not going to help either. Then I try substitution. Actually, if I do u equals 1 plus x squared, then that x would be nearly the derivative. So substitution is a good idea, and I already did this example. Didn't I? So I do substitution, and I'm going to get whatever I get, what, a half of ln x squared plus 1. Many lecturers in maths and engineering and various other places are able to do this without doing substitution. They have a rule in their head that says if I see the derivative on the top and a thing on the bottom and its derivative on the top, they skip straight to the ln. And it's okay to do that if you're familiar with that approach. But if you need substitution, that's fine too. But if you do engineering maths or differential equations next year, it might be worth learning that particular approach. And there is the answer. So that's the 1 times approach. Just note that sometimes you have to do that integral by another method. Okay? And then there's the go round in circles approach. Now, I know that I already said that the best plan for this is trig identity, but I just want to show you that if you hadn't chosen trig identity and had chosen by parts instead, that would have worked out okay. Okay, so let's just have a look. I can only integrate what I can, and it's possible to integrate both of those, so that's okay. And I need to make it simpler, but if I differentiate either of those, it'll still be trig, and so that's not going to be any simpler, and so therefore I can choose whichever ones I want. So since it's easier to integrate cos than it is to integrate sine, I could pick that one, but I guess sine x is easier to integrate than cos 3x, so we just have to pick something. So I might as well do it in the order that it's traditionally done. So f is sine x according to my diagram, and g dashed is cos 3x. The integral of cos 3x would be a third of sine 3x. The derivative of sine x would be cos x. And that's nice, there's no minuses. That was a good plan, that one. So f is sine x. G is a third of sine 3x. F dashed, oh whoops. F dashed is cos x, and G is still a third of sine 3x. My issue is, I still can't do it. I still can't use substitution. Okay, so by parts again then. Now I've already used F and G, so I'm going to use H and K because they're my next go-to letters. Now I'm going to have to make my choice again, but I really need to be careful because if I make my choice wrong, I'll just undo what I just did. So I need to make sure that I put my dashes in the same order that I had before. So the second one has to be the one with the dash this time, the same as it was before, because otherwise if I integrate the sine 3x, if I integrate the cos x, I'll just be going back to where I was. I need to go forward. Okay, so just a second, we need some space somewhere. So what have we got? We've got that h is a third cos x, so h dashed is a third minus a third sine x, and I've got that k dashed is sine 3x, and so k must be a third of cos minus a third cos 3x. Wow! So h is a third cos x, k is minus a third cos 3x, h dashed is minus a third sine 3x, and k is minus a third cos, no, have I done that wrong? H dashed sine x, cos 3x dx. Let's just expand that out so it's not bad. I'm sorry for my poor writing there. Plus a ninth of cos x cos 3x plus a ninth and it's still wrong, right? I still haven't got anything that I can deal with, but I have actually come back to where I started from. Have I done something wrong? Yeah. I have actually come... Now let me just change that sentence. I have come forward to where I started from. Okay, I've gone forwards and ended up back at the beginning. Okay, that's the key. Going round in circles, that's what we want to do. We actually want to come back to where we started, because let's just... Right, root sine x cos 3x has come to this, and I've got a sine x cos 3x. If I move this over there, I'll have two of them. So, let's call this I, just to make my life easier. And then we get that I is a third of sine x sine 3x plus a ninth of cos x cos 3x plus a ninth of I, because I can bring that ninth out the front. And if I move this over that side, I'll have I minus a ninth of I, so I'll have 8 ninths of I. Technically I should put a plus c here at the point when my integral has disappeared, but I'll reserve that for a minute. And then to get my integral, I'll just have to divide by that number. So I'll get 9/8 of this, which will leave me with 3/8. Magic! Okay, so what happened here is this went over there, and then this I divided by that. Okay.
Excuse me.
Yep.
What happened with, right at the top of the screen, what happened with your negatives? You've got 3 negatives for the integral part?
That's a plus.
Oh.
Because there were already 2 minuses, so they cancelled each other out. So let me just check that. H dash was minus a third. Oh no, correct theirs. Was minus a third sine x. And K was minus a third, so they became a plus a ninth. Yeah, okay. Yep.
How likely is it we'll get something this long-winded in the exam? Because it's only a 2-hour exam, isn't it?
Yep. Okay, so this long-windedness would happen if they gave you a reduction formula question. It is unlikely to get both a reduction formula and a trig substitution in the same exam. Okay, so you'll find that the crazy integral things, those last 3, the trig substitution, by reduction formula, the partial fractions, have the tendency to only get one of them. But of course it could be any one of them, so you have to know all of them. Yes?
How do you know if you've gone around in circles too much?
You need to really pay attention to the moment it becomes the same as what you started with.
But would it be like, is there a way of knowing that, oh, I've done this 3 times around, I've probably gone too far?
It's usually twice.
It's usually twice. But it could be more?
No, it's usually twice or once.
Oh, okay. So generally, if you've done 3 times, you've done something wrong.
Yeah, so if you've done your integration by parts 3 times and it hasn't, and it's not looking like it's hopeful to get simpler. So if you start with x to the 4 e to the x, you're going to have to keep doing it until the x disappears. But if you end up, if it's not looking like it's getting simpler along the way, if you've done it 3 times, then going around in circles probably isn't going to help. Yes?
Is the exam likely to progress the way you're teaching us these methods, or are we going to have like U substitution at the end and then like some random reduction at the start?
The exam is probably not going to be in any particular order. But if you, on each question separately, if you think in your head, let's try this, let's try this, let's try this, you will get to the one you need. Okay, that's the whole point of this. So last year or the year before, there was just a question about integration. It had like A, B, C, D, and it just had 4 integrals there, and you just had to do them, and they were all by different methods. And the third one was the one that was just rewrite, was just expand the brackets, and not the first. So you've just got to know. Yeah. Okay. While I'm at it, let's do reduction formula with the next 15 minutes. Right. So let's just take stock of where we've been. So when you have an integral, you should check to see if you can just do it. Don't leap straight into substitution or by parts. You should try expanding the brackets or factorising if that might help, or using a trig identity, especially if there's things involving trig. Substitution is the next thing to try. You should always try substitution, especially things that look like they're by parts but have substitution sort of feeling as well. You should try the substitution first because it'll be easier. So an example of that, I won't do it because there's an example of it somewhere, but if you saw this, x cubed e to the x squared, it's two things multiplied together, so it could be by parts, but there is something inside another function, and so substitution is also something you could try. Try the substitution first. Okay, so you want to go u equals x squared and see what happens then. You will have to do by parts, but if you do it after the substitution, everything will be a little easier. So you'll have to do substitution, and then, while everything is in terms of u, by parts. Give that one a try. There is an example like that. I've got some written examples. I don't have videos of the substitution in by parts yet, but I do have written examples of how to do this sort of thing to do both. There was an assignment question that had both integration by substitution and integration by parts. It's easier to do it with the substitution first. Okay, now where was I? We were seeing where we'd been. Okay, so we've tried substitution, we've tried by parts. We know about trig substitution, so we've looked at all of them and gone, crap, it doesn't work, so we tried trig substitution, especially because we noticed there was a root in it. And there are two other methods. Reduction formula is one of them, and it's specifically designed for when you see really huge powers. Well, where huge means, 6. Technically, you could do it with higher powers if you had a computer to help you. And you could if you wanted. And the point is that a lot of these methods were invented before computers. So they had to have a method of doing it at all, because having a method is better than not having a method. So reduction formulas, I have put them level with by parts because you tend to use by parts to do them. Okay? And there are two sides to reduction formulas. There's making reduction formulas and there's using reduction formulas. And in general in an exam, you're not usually asked to do both. Okay? You're not usually asked to both make and use a reduction formula. It's one or the other. And usually if you do have to make them, they'll tell you what the answer should be so that you know where you're headed. That's just tradition, just gleaned from the last last 15 years of exams. That's generally how it's done. But new lecturers are always a little bit of an unknown quantity. Yes?
So can you do a reduction formula without doing parts?
Yes.
Okay, is that something we need to know?
You can do it by trig identity. So it's unlikely to happen, so it's probably okay to leave it. There is a written example in my thing of doing it by trig identity. And it usually, if you've got sines and secs, it will be, not sines, tans and sec, then it will usually be trig identity that does it, not by parts. So that's the general idea. But it is possible to do it without by parts, but only under really special circumstances. Okay, back. So the reason why this going round in circles concept is so important is because that's what the reduction formulas are created with. Reduction formulas are created by going round in circles with by parts. And that means that you have to really be focused, because the moment you've made a new integral, you need to check if it's at all similar to the thing you started with. Especially, you also need to check if just a tiny little bit of rewriting will make it similar to the thing that you started with. Okay, so I'm going to do the using first, and then the making. Just give me a second. Now, I would not be at all offended if you have to leave, because I have booked Frenchy all day, and I'm happy to stay here all day if you want to. But if you have to go, or you want to just go eat something or something, feel free. So just, I won't be offended. So I'm just trying to find a good reduction formula in my examples. No, I have to make one first. Okay. Okay, so my making of reduction formulas. So your classic reduction formula has a big power in it. It'll sometimes be like an e to the something or an x to the something. But the classic ones are the sines and causes, and they're the ones that normally appear in exams. Okay. So the whole point of a reduction formula is you won't normally see when attempting to solve an actual real problem in engineering or science or something, you won't see it with an n. It'll be sine x to the 5, something like that. But the purpose of a reduction formula is to find a formula that will do your integration by parts for you. Okay, you only, because I could do this by integration by parts, by sticking a 1 there, or possibly splitting, if I had sine to the 5, I could split it into sine to the 4 and sine, and use integration by parts on that. I could do it by integration by parts, but I would have to do it like 4 times. So what I'm going to do, is I'm going to find a formula that will do the integration by parts for me, no matter what the n is, so that I only have to do the integration by parts calculation once, and then I can just use the formula for the rest. So the first step is to call your integral a name so that you can use it later. And I'm going to call it I number n. This is integral number n. Okay, it's the integral of sine x to the n. And then I'm going to do a reduction formula like so. So it's usually, we want to do it by parts. And the classic trick with sine, so I could do the 1 times, right? 1 times sine x to the n, but what that's going to do is that's going to introduce an x, and x sine x to the n is not happy. So we're going to try and do it with only using trig stuff, because our aim is to get back to something that looks the same as this. So I'm going to split off one of my sines. Okay? So it's sine x to the n minus 1. So already this is only going to work if n is at least 1. But then why would you bother? So this is our first step. We're going to split it. So let's just split. Okay, and then we're going to do our integration by parts. Okay. Well, I do not know how to integrate sine x to the n minus 1, so I can't integrate that one, so this one has to have the dash. So the integral of sine x is minus cos x. G is sine x. I didn't leave myself enough space. G is sine x to the n minus 1. So g dash will be n minus 1 sine x to the n minus 1 times the derivative of sine x because of the chain rule, so that'll be cos x. So let's see. F is minus cos x.
Excuse me.
Yep.
When you sine and take 1, don't you take another 1? Because you know how when you do the derivative, don't you go like so sine
Oh, you're right.
x?
2. Thank you. So easy to make mistakes in these things. So, see, that's why exams are only 2 hours long, right? They used to be 3 hours. But, yeah, you get really tired. Which is why I probably should have brought something to eat. Good tip for the exam. Bring something to eat. Don't do it aloud. That'll tire you out real fast. So, G is sine x to the n minus 1. F is minus cos x. G dashed is n minus 1. Sine x n minus 2 cos x. Okay, so that's where I'm up to. Now I could, if I wanted to, do integration by parts again, but it's going to get really ugly because I'd have to integrate cos squared, which means I have to use a trig identity, and it's just going to turn to just crap. So what we're going to do is we're going to use a trig identity instead, because trig identities are easier when you've got trig. I noticed that if I had that cos squared and replaced it with 1 minus sine squared, then my integral would turn into something that involves only sine, which is what my original integral looked like. So that's my idea behind it. So this bit here, that was my by parts. Now what I'm going to do is I'm going to use a trig identity. So that cos x squared is going to be replaced with a 1 minus sine x squared. And now everything's in terms of sine, which is good because my original integral didn't have any causes in it, so I need to somehow get rid of the causes at some point. I'm going to expand this out. So let's see. I can expand this and this into here, so I'll get the integral of n minus 1 sine x to the n minus 2 minus the integral of n minus 1 sine x squared times sine x to the n minus 2, which would be sine x to the n, like that. I skipped several steps there. Not usually a good plan in an exam. Probably best to just do several steps. Now here's the key. Without the n minus 1, this is the same as what I started with, except it's got an n minus 2 instead of n minus 1. So that means it must be I with an n minus 2 instead of an n minus 1. Okay, because the n minus 1 can be brought out the front of the integral. And this is n minus 1. Without that, that is what I started with. That's precisely what I started with. Okay. And here's the magic. Remember our go round in circles thing? We have come back to where we started. This in was what we started with. The in minus 2 is a little bit further down, but it's pretty similar. I'm going to move this back to the other side. So I'm just going to chuck this in here so it's easier to see. There's my in. I've got n minus 1 of them here, and I'm going to move them over there. So I'll have 1 and another n minus 1, which leaves me with n. and just keep track of that. I've got one in here, and I put on another n minus 1, so that lets me with n lots of in. And I can divide by the n, and I'll have my reduction formula. That is a reduction formula. It's supposed to have an n minus 2. Sometimes it's an n minus 1, depending on the sorts of functions, but trigonometry stuff, it tends to go down by 2s. So if you start with something that's got trig in it, you'll only have an n minus 2 when you get to your next stage. If you start with something with an ln, it'll usually only go down by 1. That's your reduction formula. That's as far as we need to go for making a reduction formula. And it's often in an exam they will say, let in be equal to that, show that this is true, and they'll give you the reduction formula so that you know where you're headed. Okay. Using it is a different story. I'm going to do 2 examples of this with that reduction formula. I'll do a nice small one so it doesn't take too long. Maybe one more. So find the integral of sine x all to the 7 dx. Okay, so that's I7, right? My formula tells me if I put 7 in for n, I'll get minus 1 over 7 cos x sine x to the 6 plus 6 over 7 I5. And then I need to figure out what I5 was using the same formula. I'll get I5 is minus 1 over 5 cos x sine x to the 4 plus 4 over 5 I3. And then I could put the 3 in and I could figure out what I3 was, and eventually I'd get somewhere that I knew what to do. And I would have to stop eventually because I'm not going to get sine x to the minus 7. That's not helpful. So we want to get to the lowest possible one that we know how to do. So the smallest one we know how to do with this would be when the power is 1, because the integral of sine x I can do, it's minus cos x. Okay? So that's where I'm headed. I'm going to get all the way down to I1. The reason I say all this without writing it down is because it's much easier to, at least for me, in an exam situation where there's lots of minuses to go astray, it's much easier to start from the bottom and work your way up than it is to start at 7 and work your way down. You just have to know that that's where you're headed. So I just have this little diagram on the side that says, well, I'm at 7, it'll go down to 5, it'll go down to 3, it'll go down to 1. I can do 1, and so I'm going to start there. So traditionally, you have to start with this.
Sorry, how do you know it's going down by 2?
Because here it's got n minus 2. So if it was only going down by 1, I'd go all the way down to 0, because that's the simplest one. And if I had started at sine x to the 6, then because it goes down by 2s, I would go down to 0, because that's the simplest one. But I can't get all the way to 0, because I'm only going down by 2s. Yes, so the point is it goes down by 2s because of the n minus 2 here. Okay, so I1 is the integral of sine x to the 1 dx. And the base one you have to do by a different method. Okay, so, and I know how to do the integral of sine x, it's minus cos x. And I'm going to leave all my plus c's off, because it doesn't really matter until we get to the end. Though, I'm going to put it in because force of habit. Okay, so, I've started at I1. Okay, got that one, tick. I3 is the next one, I'll figure that one out. So according to the reduction formula, minus 1 over, and n is 3, cos x, sine x, and n minus 1, well, n is 3, so that's 2, plus n minus 1, I, and n minus 2 is 1. So I put the 3 into my formula, and it's told me how to do my reduction, how to get it down to I1. And I know what I1 is. It's cos x. So I can sub that in there. And then I5, well, according to the reduction formula, it's minus a fifth of cos x sine x to the 5 minus 1, which is 4, plus 5 minus 1, which is 4 fifths of I3, because it goes down by 2. And I know what I3 is. It's this. And so I sub that in. So it'll be 4 fifths of that, which will be minus 4 fifteenths of cos x sine x squared, and 4 fifths of that, which will be minus 8 fifteenths of cos x. And that's I5. And you can see where this is headed. I7 would be minus a seventh cos x sine x to the 6 plus 6 sevenths of I5. And I5 is this, so I sub that in. Oh wow, so 6 sevenths of that would be minus 35ths of cos x sine x to the 4. 6 sevenths of that would be minus 24. Wow! 105 cos x sine x squared. And 6 sevenths of that would be 8 times 6 would be 48 105ths of cos x plus c. And that's the answer I was hoping. Well, it's awful, but that's what I was getting to, I7. So doing it one step at a time and subbing each of them into the next, I find easier. It is unlikely they will expect you to use it more than twice, so it would normally be an I5 rather than an I7. But, yeah. Okay, I do have another example to show you. So starting from the bottom is better. It's like Harry McClary, you know. If you don't know Harry McClary, go read it. It's an excellent book. He had his birthday last year. I think he was 20. So that's how I use reduction formulas. But I do have another one. What if it's a definite integral? Sorry? Yeah. So someone said, do it indefinitely and then evaluate. Well, you can actually make a reduction formula directly for the definite integral, which is quicker, and I'll show you how. So we know that in is minus 1 over n cos x to the sine x n minus 1 plus n minus 1 over n I n minus 2. Why don't we let dn for definite integral be the definite integral from 0 to pi on 2 of sine x to the n dx. Then all of these would be definite integral things. So I would get that dn would be the result of a definite integral plus n minus 1 over n and a definite integral instead of an ordinary integral. So any INs become DNs. Anything that's not part of an IN has to have its square brackets. And then when I sub this in, Cos of pi on 2 is 0. Sine of 0 is 0. So this is 0. And I have a way simpler formula. And that, my friends, is totally easier. So I'll do the same trick. I know that I'm at 8, and that's going to eventually go down by 2's, and I'll get to 0. I'm going to have to do 0 separately by a different method, but that's where I need to start. So d0 is the integral from 0 to pi on 2 of sine x to the 0 dx, and anything to the 0 is 1. So I'll get pi on 2 minus 0, which is pi on 2. Okay, so it goes up by 2's because it's got an n minus 2. So d2, according to the formula, will be 2 minus 1, which is 1. So this is the formula here. 2 minus 1, which is 1, over 2 times d0, but d0 was pi on 2.
Could you please move the page down a little bit?
Yep. Oh no! What the hell? Ah! I pressed something. No. Well, yesterday, if you jiggle this plug, it goes blue. That's blue now. Okay, so that's a half of pi on 2, and which is pi on 4. And d4 would be 3 over 4 times d2, which would be 3 over 4 times pi on 4, which would be 3 pi on 16, and so on. Even better than this, I could, if I wanted to, just abstract my formula to realise that there's a pattern here, and I could figure out d anything. Right? So d8 should be 7/8 of d6, and d6 would be 5/6 of d4, and d4 would be 3/4 of d2, and d2 would be 1/2 of d0, and so I could just figure out whatever that is. It's not pretty. Okay, so I could skip a couple, right? And I could do d20 if I wanted by that method and just say using the pattern, right? Okay, it is okay to do that. So a definite integral formula is way quicker than finding out the big one and then subbing in. So, yeah.
Does it usually work out that neatly?
For sine and cos, yes, and they are likely to be the ones in your exam. It is possible for it to be less neat than that. There's a worked example in the written worked example book that's online that uses like ln or e or something, and it's actually the definite integral formula is like 1 minus d naught, like 1 minus n d naught by n dn minus 1, something like that. So you might have an example where I think it was that, dn minus 1. And so it's a little harder to follow through, and so it's easy. It's best to do it one step at a time. Yeah. Cross that one out. Okay. But there's an example in your lectures specifically like this, and so it's really common for them to do the cos or something like that. Okay. Well, where have we been? So we're now, yeah, thank you. We're now up to here. We did trig substitution. The only thing left is the last two. So I might as well just keep talking. If you all leave, I'll just do it to an empty room. So, right. It's really important with something that has a lot of techniques to have some nice buzzwords for yourself. That if you say it in the right way, it will remember what to do. So that's why I have these things here. Watch for the original integral. I'll have to rewrite or go around in circles. And just to remind yourself that you're going to have to bring that across. And the start from the bottom is a really good strategy. The only thing left I want to do is partial fractions. Here we go. Feel free to go if you need to. I'll give you a minute. Okay. The purpose of partial fractions is to rewrite things. It's not technically a method of doing integrals at all. It's a method of rewriting rational functions. So you will find, if you do Engineering Maths 2B, or something in physics or some other things in maths, but especially Engineering Maths 2B, you will find that partial fractions will come back and you won't be using them to do integrals. You'll just be using them to separate fractions. So the whole purpose of them is to separate your fraction into other fractions that are easier to deal with. Okay, but the point is that the fractions you separated into are ones that you are able to integrate by other methods. Okay, so it's a really fancy way of rewriting things. So you don't do the rewriting inside your integral, you do it, separately.
Thank you.
You do it separately. So, yay. There are three things that happen, okay, that you need to know about in order to do this effectively. One is you need to be able to do polynomial division. Two is you need to be able to split the denominator in the right way. And three, you need to be able to complete the square. Now, I've already covered the completing the square in that other example. That completing the square happens after you've split it into other fractions, okay? So we've already done a fraction where we had to complete the square and it turned out to an arctan. And that's what's going to happen. So you're going to be turning into things that either go to ln, or that use ordinary powers, or that use arctan. So that's what you'll see at the end when you do your integrals. And so there's three parts to it. Okay. Okay, so we're going to do this integral, x cubed plus x plus 1, all divided by x minus 2. Now why you would want to do this is just because we'll have an intense sense of self-actualization by knowing that we can integrate any rational function if we want to. Okay? I'm sure that there's a real reason, but you'll be better people because of it. So here we go. X cubed plus x plus 1 divided by x minus 2. The first thing you should do is see if you can actually do that division. Because if you actually do the division, it might come out to something a bit nicer. And so we need to be able to divide polynomials. So when I learned polynomial division, I couldn't remember in the slightest ordinary long division, and it doesn't help that much. So I have this nice process, and it goes like this. Make sure if every power isn't there, leave a gap so that you can remember that there's supposed to be an x squared. That's the first step. And the second step, the rest of it goes like this. So the biggest power that you see here, we divide by the biggest power that we see here. X cubed divided by x is x squared. And you put your answer above. Some people put it here in the x squared position, but I like to put it above the thing that I divided. And that's step one. So step 2 is to take that thing that you just made and multiply it by this and put it underneath. Okay, so it was divide, multiply, and now we subtract what we've got. And subtract. So x cubed minus x cubed is 0, 0 minus 2 minus 2x squared is plus 2x squared, x minus 0 is x, 1 minus 0 is 1. Now, some people only bring down some of those terms at the top. I bring them all down because otherwise I forget and I get it wrong. So I like to have strategies where I don't have to remember too much all at once. So now it's a brand new division problem. I ignore everything I've done before. Smaller fingers. Everything I've done before, and I go this divided by that, and I write it here. So the 2x squared divided by the x is 2x. So I've done the divide. Now the multiply, 2x times x minus 2, so the 2x times the x is 2x squared. The 2x times the minus 2 is minus 4x. And now I subtract. 2x squared minus 2x squared is 0. X minus minus 4x is 5x. And now I've got a new one and I'll just do that. Okay, so 5x divided by x is 5. That's the divide. The multiplier, 5 times x minus 2 is 5x minus 10. And now I subtract. 5x minus 5x is 0. 1 minus 10 is 11. And then I attempt to divide. 11 divided by x, no, can't do that. I've run out of polynomials. That's going to give me 11 over x, and that's not helpful. So I'm going to leave it. But actually I do that division eventually. So what this tells me is that this divided by this is this, that left over. So I have that x cubed plus x plus 1 divided by x minus 2 is x squared plus 2x plus 5 plus 11 x minus 2ths. So you know how I said I don't do the division at the end? I actually do. At the very end, when you get this being smaller degree than that, you really do put it in. And you just leave it as it is. So that means that when I do my integral, I can now do every part of that. X squared goes up to x cubed and I divide by the new power. 2x goes up to x squared and I divide by the new power. 5 goes up to 5x. And 11 over x minus 2, well, it will still have an 11. 1 over x would have given me ln x, but it's x minus 2, so it will be ln x minus 2. And I would have to divide by the constant derivative, which is 1 anyway, so it's all okay. Technically, the polynomial division is not really part of the integral at all. It's just my way of rewriting what was there. So that's the first step. If the top has a bigger power than the bottom, you're supposed to do polynomial division. So you've got a polynomial, this bit here, and then fraction at the end. Oh, I should, yep.
In this case, we're sort of lucky that you had an ln2 when you integrated it, like 11 over x minus 2 to get ln when you integrated it.
What do you mean by lucky?
Like, because if you're dividing by a bigger power...
Yeah, so if I was dividing by, say, x squared something, then I would be left with something that I would have to do this next stage on.
Okay.
So if I had x cubed plus x plus 1 on x squared minus 2, then I would have to, once I got to the end of my integral and I'd have like 11 over x squared minus 2, I would have to, on that bit, do this splitting the denominator. So splitting the denominator, they don't generally ask you to do both in an exam, but it's not impossible. So splitting the denominator means that I can get any fraction, as long as the top has a smaller degree than the bottom, I can split it into separate fractions if I factorise the denominator first. I have to factorise the denominator. And what it'll do is it'll factorise into, you know, for example, you'll be able to factorise it into something like that, okay? Yeah, so their exam writers are common for just giving you the factorised version to begin with, okay? Or they'll give you one that's fairly simple. So it needs to be factorised, and then for each separate piece, you have to include things in your partial fraction so you know what the final integral will look like, except for the constants. I can't think of another word for it, but write the form down. So, for example, for that one there, if that was my denominator, my final form for each linear term, it would have constant over that, and I need to do constant over that squared, and constant over that cubed, and constant over that however many, all the way up to whatever power I've actually got. And for each quadratic term, I need to have constant, a linear thing over that. So this would be a over x, that's for this one, and a b over x squared. I'm going to run out of letters pretty fast, but this one would have a c over x minus 1, and a d over x minus 1 squared, and an e over x minus 1 cubed, and an f over x minus 1 to the 4, and a g over x minus 1 to the 5, because that's how many powers there are in the original. It would be an awful exam writer who gave that to you, but I just wanted to make the point that this power is 5, so I'm going to need 1 for all of them. The x squared plus 1, there are multiple ways of dealing with this, but the traditional way is to go that. Now this is for quadratics that don't factorise. So x squared plus 1, I would have to use complex numbers to do that, so I just leave it. Okay? And then the x plus 5 will need one of its own. And it'll only have 1 because it's only there once. So that's the process for writing the form down. In past exams, sometimes they have a question that just asks you, what is the form? And they don't ask you to solve it, they just ask you what it is. And I should say that if this quadratic factor had been squared, I would have had to have 1 for that as well. Okay, so everything has to be there for every power of what's there. Now, if you were actually expected to do the integral, this would not happen because you haven't been taught how to deal with that integral. Unless, of course, the k came out as 0 and then you could use ordinary substitution. So I just wanted to point that out. If you're expected to actually do it, then certain things will have been set up so it's possible for you personally to do it, but it is possible for them to just give you a factorised thing and say, what's the form? Okay. That's how you split the denominator, but it's not how you actually figure out what the constants are. But even without the constants, even without knowing them, I can write down the integral, which is a good strategy for the exam. If you don't have time to figure out what the A, B, C, D, E, F, G, H, I, J, K, L are, you can just write down what the integral is going to be. Okay? And I won't do it for this one because it doesn't have that. But these ones need to be dealt with. So, and the next thing is, find the constants. And then 4 is integrate. Okay, I just want to do some things with this integrating here. If you have something over x minus 1 squared, that's something times x minus 1 to the minus 2, which will integrate to give power up by 1, divide by new power. People tend to forget that that's something that's okay to do. Okay, so all the powers beyond minus 1 you can do by ordinary power methods. Okay? I just wanted to point that out. And that's arctan, right? You're supposed to, if the bottom doesn't factorise, you're supposed to complete the square and use arctan. So, for example, if it was x squared plus 10x plus 26, you'd be able to use arctan. Okay, just that's the point with the integrating. And don't forget that ln have absolute values. They probably won't make doc marks if you don't, but it does make a difference. Okay, so now I should just do the how do you find the constants. So finding those constants. This is the tricky bit. So they often don't do it for anything that's really all that complicated. But why don't I do this one? So I'll do the whole process. Okay, so here's an example. I've got x plus 1 on the top. I've got x squared plus 1x minus 2 on the bottom. If you would really check to make sure the x plus 1 didn't cancel with something on the bottom. That would totally make it easier, but it doesn't. And then I'd also check to see if the power on the top is smaller than the power on the bottom, and the power on the bottom in total is 4, because there's 1 from the x, 2 from the x squared plus 1, and 1 from the x minus 2. So yeah, polynomial division is not going to be necessary, which is great, because I would have had to expand this out, and it just would have been crap. So we're going to continue this way, and we're going to go, we're going to say, well, I know the form. It's something on x plus something on x squared plus 1 plus something on x minus 2. That's my form. And that's the fraction it's going to be split into. None of them are to any higher powers than that, so I'm good. Am I going to put 1 in? No. Okay. So this is supposed to be equal to x plus 1 over x squared plus 1, x minus 2. That's what it's supposed to be equal to. They're supposed to be the same thing but written in different ways. The whole point is rewriting. So I need to make them equal so that I can tell what the A's and the A, B, and C and D are. Oh, incidentally, the reason why you have to use a certain form is because it might not be possible to find the A, B's and C's and T's to make it work unless you write it in the correct form. Coincidentally, it might work sometimes, but sometimes it won't unless you use the right form. So I'm going to put it over a common denominator so that I can make it into what I need. So this A has an x already. I need to make it this denominator, not just a common denominator, the one that we had there. So I need this one, I need that to be added to it. So I'm going to have a x squared plus 1 x plus 2, because I'm going to times top and bottom of this by whatever's left except the x. Oh, minus 2. Okay, and the next step is this one, it has the x squared plus 1 already, so I'm going to have to multiply by whatever's left. And the d already has the x minus 2, so it's going to have to be multiplied by this. And all of that is supposed to be equal to my original integral. Now what you're supposed to do is you're supposed to equate the numerators now, and you're supposed to expand out the numerator so that you can equate coefficients. There is another method. You can sub in values of x, and it will make some of them go away, which is often a good plan as well. So this is probably more complicated than what you would be given in an exam, but I just wanted to point it out. And so this is supposed to be x plus 1. Okay? So I've got choices at this point. I can sub in values of x. So for example, if I sub in x equals 0, that and that will go away, and that will be 1 minus 2, so I'll get minus 2a equals 1. So I can sub in values of x. And I can also try and expand it out and equate the coefficients of x as well, of x squared and whatever. So I get either choice, and I might not have enough things to sub in to get me what I need. So yes, there is a shortcut to finding the coefficients. So constant term. If I just look, the constant term would have to be made by choosing these two constant terms. So it would be minus 2a. The constant term here could only be made by choosing constant terms, and this one doesn't have a constant term in that one there, so that doesn't contribute a constant term, and neither does this one. So I get, for the constant terms, that, so a is minus a half. For the x term, I need to make an x. So I'm not going to make an x out of that x squared, so I can ignore that and pretend it's not there. And then I'm only going to be able to make an x by going a times 1 times x, so that's going to be ax. And I'm going to continue that way, but it's easier to just expand it out because I'm going to get that wrong. So, yeah, crap. So you just have to expand it out, and it's going to be painful, and it's going to be awful, and it's going to just cause pain. So we've got x cubed minus 2x squared plus x minus 2. We've got, I'll leave the x to later, bx squared minus 2bx plus cx minus 2c, and we've got dx cubed plus dx. That was expanding out. So we've got bx cubed minus 2bx squared plus cx squared minus 2cx plus dx cubed plus dx equals x plus 1. Now I can equate coefficients. So my constant, the only constant I have is this one, and it's equal to that. My x term, there's an x there, so that's giving me an a. And there's an x here, that's a minus 2c. And there's an x here, so that's a d. And that's coming out to 1x. So I've got 1x. And my x squared term, I've got minus 2a from that one, a minus 2b from that one, a c from that one, and that's it. And there isn't an x squared term, so that's 0. And the x cubed, ax cubed plus bx cubed plus dx cubed is 0 as well. So I get these 4 equations in 4 unknowns, and I solve them simultaneously to figure out what the a, b, c, and d are. And you can do that using matrices if you want. Right, so you can go like a, b, c, d. I've got minus 2a's, and here's my answers is 1. So, and none of them, that's the first equation. 1a minus 2c and 1d is also 1. Minus 2a, minus 2b and 1c and no d's is 0. 1a and 1b and 1d is 0, and I can do reduced echelon form, and it will tell me what the a, b, c, and d are. And then I sub it all back in to the original, and I can do my integral, right? Yay! Woohoo! So life ends, and we go. I think I might do the calculus, the algebra part of the exam now. You can actually. One of the nice things you can do if you've got something like MATLAB is you can just sub in like all these different values for x, so that you get equations from them and then get it to solve it. It's really cool, and I presume that that's what our Wolfram Alpha's doing. Okay, so I should just do a simple one so that you can see it happen. 1 over x squared minus 1 dx, classic. You're supposed to factorise the denominator, which I can do because x squared minus 1 is the difference of two squares. And then you're supposed to write the form that you would see. So this is a over x plus 1 plus b over x minus 1 because they're only there once each. I can do the common denominator. So my common denominator is x plus 1, x minus 1. My a currently already has the x plus 1, so it's going to need an x minus 1. My b's currently already got the x minus 1, so it's going to need an x plus 1. And so now I can equate my numerators. 1 is a x minus 1 plus b x plus 1. So that's ax minus a plus bx plus b. And so from my constant terms, I get that minus a plus b is 1, because that's the constant here. From my x terms, I've got a plus b is 0, because there's no x term here. And so therefore from this I can get that b is the same as minus a. And then I sub that in, subbing to number 1, and I get that minus a equals 1. So a is minus 2a is 1, so a is minus a half. And since b is minus a, that means that b must be minus a half, which is plus a half. So that's the quick one, and it's the one that you would, something like that, you'd likely to see in an exam. And then you would go, therefore my 1 over x squared minus 1 is actually, a was minus a half, and b was plus a half. And so when I integrate, the minus a half will still be there, and I'll have ln of x plus 1. The plus a half will still be there, and I'll have ln of x minus 1. So that's the classic. And you'll notice if you ask Wolfram Alpha to do this, it will combine all those ln's into one big ln usually. And so it'll bring the half out the front, and then it will turn that subtraction into a division. Should just point that out. Of course, you won't have Wolfram Alpha in the exam, so that's irrelevant. But just while you're trying to get something to check your answers, just good to know that. So that's partial fractions. There are actually really clever methods of dealing with some of the things that come out of partial fractions, but you don't have to be that clever. But do remember that every one of those single integrals, you need to go back to the original methods. So it's a divide by the constant derivative, or substitution might be necessary. So you might see an x over x squared plus 1, which would be a substitution. That is all the techniques of integration except do it numerically, but I'm way too tired. So I will leave. Last time I did this, 3 years ago, I did the do it numerically first. So I will leave that there and say the first section of that is the numerical integration, so that you can look at the video from last time. Thank you very much. I'll probably do another one later in the week.